Yeah, no, I appreciate it. Yeah, no, it's good. Okay, so we're going to continue our discussion of how an inner product and the ideas of orthogonality and normalization impacts the study of linear operators that are acting on vector spaces. We've obviously used it to explore properties of vector spaces, and in particular bases of vector spaces and their orthogonal counterparts. We've done a lot with that. We've kind of touched on this at the end of the last lecture. But now we're actually going to explore in depth the use of an inner product for linear transformations, and we're going to find out some really interesting results. Starting with this one, which I will just come back to again and again and again, so I'm going to write it down and leave it up here. And this is a theorem, a linear transformation A on an inner product space so this is acting on a vector space for which there is defined an inner product, and it can be a general inner product on a general vector space. It doesn't have to be, you know, the dot product. It can be any of these inner products. Is equal to 0 if and only if, and I'm using smooth brackets, not these angled things, so sorry about that. If the inner product of x and ay equals 0 for all x and y. Okay? Now I'm not going to prove this, but it should be fairly intuitive. But it is a result that we're going to use throughout what we're going to talk about today. So I'll just leave it up there. Okay. So with that in mind, one of the first sort of matrixy topics that we can explore how the inner product impacts is the idea of a determinant, because the determinant of a matrix, or the matrix representation of a linear operation, I should say. We're going to start with the matrix language, but then we're going to go back to the more generalized, generally defined abstract definitions of linear transformations. But we're going to start out with the determinant, which is obviously an operation on a matrix, and then we'll generalize later. But remember that the determinant of a matrix tells us a lot of useful stuff, whether it's invertible, tells us information about the eigenvalues and so forth. So we can ask, what does the orthogonality and normalization do to find the determinant? So consider the following matrix. So consider the matrix A, A11, A12, dot, 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 A21, dot, 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 dot. Okay? Now suppose this matrix had a very special form where I could call it A1, A2, dot, 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 where each of the A's in this case are orthogonal vectors. Okay? So this thing is going to have n components, where n is just the dimension of its matrix. This is going to be a vector with n components this way, and then I'll have n of them, so this will obviously fill out an n by n matrix. But each vector is going to be orthogonal to all the other vectors. Okay. This is just a very special matrix. Very special. Okay. Now, let's do some playing around with it. First of all, clearly, if I take A times the adjoint of A, which is the complex conjugate transpose, and I consider the ikth element of that, then this is going to be basically A star transpose ik. All right? And then actually working in terms of the elements of the thing, we can say, okay, this is sum over j, aij, ajk, whoops, star transpose. Okay. Now, to transpose an element, we have to just swap the indices. And so rearranging these things, this is going to give us sum over j, star aij. Okay. Now, what does this look like? Remember, the first index on these is the row label. So this is taking row K and row I, and it's summing over the second index, which is basically labeling the elements of the row. And it's summing over them. So what is this doing? It's doing the inner product. Okay? So it turns out the elements of this are related to the inner products of these vectors. But these are orthogonal vectors. Okay? So we can argue that this is really just the inner product of the kth row with the ith row, but they're orthogonal, so we know that this is going to be the delta function over ki times the magnitude of the vector. They're not normalized. We could normalize them, but we'll just take them as non-normalized, so their magnitude is going to sit there. Okay? All right. So this means that if we actually go away from individual elements and blow it up to the entire thing, that a dagger is just going to be a matrix composed of zeros and then non-zero diagonal elements. Okay? This is a very special matrix, so the fact that it comes out like this is not too weird. However, now we can make an argument. The determinant of a dagger Hunter, nice to. What's the determinant of this matrix? Yeah. This is a super easy determinant to make. Look, if I gave you a bunch of matrices and said, find the determinants of all of them, and this is one of them, this is the first one you pick. Okay? So that determinant's super easy to find. But now recall that the determinant of A is equal to the determinant of A dagger star, because this is just the determinant of A transpose, but the determinant of A transpose is the same as the determinant of A, where transposition is just flipping everything around the diagonal. So dagger star is just transpose. Dagger is transpose star, and if you're starring that, then you're transposing starring. It's nothing, okay? Now this tells us that the determinant of A star is the determinant of A transpose, and the determinant of AB is the determinant of A times the determinant of B. Okay? So together these give the following. Det A star, or sorry, A dagger. Sometimes my stars look like daggers. So this is just a standard rule for determinants of products of matrices. You can break it up into the product of the determinants. So we can take this and we can break it up into the product of the determinants. All right. Of course, this is the determinant of A dagger, so we can replace that with the determinant of A star. Okay. But this tells us that the magnitude of the determinant of A is the square root of the determinant of A times the determinant of A star. But this is just A1 times A2 dot 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 AN. Okay? So in a sense, even though A is not nearly this simple, I mean, this is a diagonal matrix, finding the determinant was super easy. We've just proven that the determinant of A itself takes this very simple form. Okay? Now, that might not be surprising. A is a ridiculously special matrix. It's a matrix where every single row corresponds to an orthogonal vector. Okay? So if this was the end of the story, you might be like, it's a really special matrix, got special properties, who cares? It's not the end of the story. Turns out we can apply this result to more general cases. So consider B to be an arbitrary matrix. Okay? Now we can still call B by a bunch of vectors, okay, just by using the row label and then realizing that each of these is an n-element row. Okay, and then we have n of them. But this is arbitrary. There's no need for orthogonality between these different vectors. Okay? However, so we're imagining that we have a collection of vectors that do not need to be orthogonal. However, if I give you a collection of vectors and they're not orthogonal, what would you do if you wanted to make them orthogonal? Seth?
You gave me a bunch of vectors that are not orthogonal and you want to make them orthogonal.
Or better yet, make them orthonormal.
Or make them orthonormal even better. Use Gram-Schmidt.
I'd Gram-Schmidt the shit out of that.
There you go.
So let's do it. Let's Gram-Schmidt the shit out of it. So if you're going to Gram-Schmidt this, first and foremost, you're going to get a different matrix. You can't just arbitrarily manipulate things in a matrix and say, it's the same matrix, okay? But we can form the Gram-Schmidt orthonormalization of this, and we know what it's going to look like. It's going to have the first element be B1 over the magnitude of B1, and the second element is going to be B2 minus the inner product of B1 over its magnitude, and I'm going to be kind of sloppy in my writing here, it's not that important, over the magnitude of B1 divided by the magnitude of what's in the numerator, et cetera, et cetera. Okay? I do have to write down one example of this thing. Let me write this a little bit. B1 over magnitude B1. Okay? And obviously, hopefully you know from the Gram-Schmidt, as we go on, every term is going to roughly have this form. You're going to take the B3 vector and then you're going to subtract off whatever you get from B1 and B2, so you're going to have more and more terms as you go down, but it's always going to start with the vector in this place, and then you're just subtracting stuff, and then you're dividing by something. Okay? That's an important structure to what the Gram-Schmidt procedure gives us. It gives us whatever you start with, minus something, divided by something. That sounds stupid, but it'll be important in just a moment. Okay? Now, let's form the matrix C. And I can call the elements of this, by the way, I can call them B1 prime, B2 prime, etc., just to give them a different label than B1 through Bn, because they're different elements. Now, if I want to form the matrix C, or I will form the matrix C, by basically taking the magnitude of each of these and multiplying it by what I get from the Gram-Schmidt. So I'm sort of unnormalizing it, if you will, okay? So this will be, this will be the magnitude of B2 minus B1 over magnitude B1, B2, B1 over magnitude B1, magnitude times B2 prime, et cetera, et cetera, et cetera. Okay? Now, obviously what this does is multiplying by these basically gets rid of what's in the denominator. Okay? So this is just going to be B1. This is going to be B2 minus B1, B1, B2 times B1 over the magnitude of B1. And I know I keep writing the same thing, but there's a reason for that. Okay? All right, here we go. You ready? is related to the original matrix by simply taking the elements of the original matrix and one row at a time subtracting something from it. Okay? Well, we're not just subtracting something from it, we're actually subtracting linear combinations of other rows. This is just a number times the row B1. Okay? And you can imagine B3 will be subtracting a number times B1 minus a number times B2. Now, if you scan back to facts about determinants, can anybody tell me how the determinant of this might be related to the determinant of that?
It'll be the same.
They're the same. Okay. So we have that det C equals det B. Okay. Now, C is composed of orthonormal vectors times a bunch of scalar multiples. Okay, the primes are orthonormal, and all I'm doing for the construction of C is I'm just multiplying it by these scalars. Okay? Well, wait a minute. If I have a matrix where one row is multiplied by a scalar, and I want to talk about how I can get that scalar out in determining the determinant, how does this work out? What's the relationship between the determinant of this matrix and the determinant of the matrix A, B, C, D?
So, times 2?
Yeah, you get a factor of 2 out. Okay. Well, wait a minute, hold on. So det C is a bunch of constants times the rows. So det C is going to basically be all of these constants pulled out. And, you know, I could write them down, but I really shouldn't. Okay. These are all multiplied together. Times the determinant of a matrix which is composed of orthonormal vectors. It's 1. Because the determinant of a matrix composed of orthogonal vectors is just the product of all of the magnitudes, but these are normalized, so it's just 1. Okay? So if we call these constants a set beta 1, beta 2, etc., then we get what is called Hadamard's inequality, which says that the determinant of B must be less than or equal to the product of the magnitudes of all of these B's. Okay? So this is Hadamard's inequality. Now, where does this come from? Mateo. Where does this inequality come from? Exactly, okay? So det C is taking this guy, and then it's taking this guy, but it's subtracting something from it. So beta 2 is definitely less than the magnitude of B2. Does that make sense? Okay. All right, any questions about this? Okay. So we have a result for determinants. Now it's time to turn our attention to some special classes. So this was arbitrary, remember? I wasn't saying anything special about that matrix. Okay, now we're going to turn to some special matrices, which play a very, very common role in your physics classes. And I'm hoping if I can get to this by the end, that we'll have sort of an umbrella pattern of what all this means and why it's important. But I got a lot of pages of notes to get through to get there, so let's just hang on and do it. All right, so recall the definition of the adjoint of a matrix. So A with elements Aij gives you an adjoint with elements that are the transpose elements. So I swap the two indices and then the complex conjugation of the transpose. Okay? So of course, a simple way to think about it is that A dagger is A transpose star. Okay, I usually write transpose as a capital T, but that kind of does look like the dagger, so we're going to use the book's notation. We'll say that twiddle is transpose, and then star is obviously what it is. Now what I want to do, this is a matrix definition of transpose. Now what I want to do is step back and give you a more general definition of a transpose. So this definition will apply to any linear operator. Yes?
Do you remember what the tilde means?
What the tilde means? It means transpose.
Oh, okay.
So that's what I just said. I usually, for transpose, I write capital T. That's the norm in my field, but in the book it's not. But these mean the same thing. They mean take it and flip all the elements around the diagonal. Okay? That's what it means. Okay. So what was I saying? So yeah, so we've got a definition, this is a definition for matrices. We want a definition for arbitrary linear transformations, but of course, whatever definition we give for linear transformations should in some way also give rise to this definition, because any linear transformation is isomorphic to a matrix. Okay, just like any vector space is isomorphic to the intervals over the correct field. Okay? So we'll see that connection in a few minutes, but we want this abstract definition, so here we go. Let A be a linear transformation. Oh, goodness, here we go. On a vector space V for every A, the linear transformation operator, and this is not a matrix, it's just the form of the operation, A dagger, such that the inner product of A acting on X with Y is equal to X acting, or inner producted with A dagger of Y. For every X and Y on the vector space V. It's called the adjoint. Okay? Or equivalently, we could say XAY equals A dagger XY for every X and Y. Okay? And you can show, and I do in my notes, how this implies this. I'm just going to skip that proof. It's pretty simple. So either statement holds. right? And this is a general definition of an adjoint. Not referencing matrices at all, but of course we should be able to derive this condition from this condition because this is the general definition. We'll do that soon. But here are some useful things that this definition satisfies, and I'll actually go through a proof of one of them just to show you how we actually do it without working with matrices. So first of all, with this definition, one can show the following are true. A plus B adjointed is A adjointed plus B adjointed. 2, the product of A and B adjointed is B adjointed A adjointed. 3, an element of the field times the transformation A adjointed is alpha star times A adjoint, and A adjointed and yet again adjointed gives me back A. Okay. So one can show using this definition that all of these hold. I'll show you one. I might show you two, but I'm not going to show you all of them. Okay, so I'm going to show you how one is true. I mean, one is obviously true for matrices, but proving that it's true for this is not quite as straightforward. So I'm going to prove that this is true for this definition, never touching matrices. Okay? If we could do it with matrices, it'd be easy, but we're not going to touch matrices. So here we go. So start with, I'll do it here. Yeah, start with x c dagger y is cxy, okay? Where c is a linear operator. Okay? Now, if c equals a plus b, then we have that x a plus b, whoops, a plus b dagger y equals the inner product of a plus b acting on x, inner product of it with y. Okay, it's just replacing c in this expression with the sum a plus b. Okay, nothing weird there. And now let's go through some arguments. First of all, this is the same as ax plus bx using the linearity of linear operators. Okay, no matrix manipulation involved. This is just part of the definition of a linear operator. Okay. Well, then we can take this and say, okay, this is ax interproducted with y plus bx interproducted with y. This is using the linearity of the inner product. Okay, the inner product is definitely defined without necessarily resorting to this matrix isomorphism. In my notes, I actually write down what properties I'm using for each of these. I'm just not going to write that on the board. Okay, now we can utilize the definition of the adjoint to move these things around. Okay, that's in the definition of the adjoint. And then we can once again use the linearity of the inner product. Okay, and then once again we can use the linearity of linear operators. Okay. Now, at the end of this, does this tell me that a plus b dagger is a dagger plus b dagger? I mean, you know, that's a bracket, that's a bracket, that's an x, that's a y, there it is. That's a bracket, that's a bracket, that's an x, that's a y, there it is. Everything else in these expressions are the same, right? So doesn't that seem to imply that they're the same? I don't have a question for you yet. What if, actually, Drew, what if y was 0? Would those two operators have to be the same?
No, because it's all the same inner product.
Yeah. Yeah, I mean, all we're saying is this inner product is equal to this inner product, and I'm asking, does that mean that this is equal to this? And in truth, not necessarily, because for example, if y was 0 or if x was 0, this inner product would be equal to this inner product even if those two things were different. Right? Everybody see that? Okay, so we can't jump to this conclusion so quickly, however, it is true. So let's be a bit more methodical. So, first of all, we can say this by saying if all of this holds for all values of x and y, okay? Because then we have this theorem. And utilizing that theorem, we can say the following. X, and let me get my self right here. Yeah, so we can first of all state the theorem as right, and if we apply it to this, then what we can say is x ay minus x by is equal to 0, but this is the inner product of x with a minus b times y, but this implies that a minus b equals 0, which of course implies that a is equal to b. So I just said this is equal to this, therefore their difference is 0. Okay? I'll just call this A and this B for simplicity. Okay, so their difference is 0, but I can go about using the linearity of both the inner product and the linear transformation to argue that that implies that any x and any y, this inner product vanishes, but that's telling me that a minus b equals 0, which tells me that a is equal to b. Okay? Where again, I'm just skirting this. I'm calling this a, I'm calling this b. Okay? Everybody follow that? And you can similarly, and notice I just proved this, number one, without touching matrices. You do not need the matrix isomorphism in order to prove all of these aspects. And you can also prove 2 and 3 and so forth. Okay, but I'm not going to go through those. All right, any questions? All right. Now, all right, now to demonstrate the connection between this definition and our matrix definition of an adjoint, we can do the following. We can say, all right, so I'm going to start with the matrix elements of a linear transformation with respect to an orthonormal basis. Okay. So remember, how your matrix appears depends critically on what basis you're using to express it. So I'm just going to pick an orthonormal basis to express the elements of my matrix. And this is an orthonormal basis set. And then what I've got is that the elements of my matrix are inner products of basis A with A acting on basis J. Okay, this is what we finished the last lecture with. All right. Then what we can argue is, all right, so Aij is, by this definition of an adjoint, A dagger xi xj. Now, one interesting thing about the inner product is if I just flip it, I get the same valued thing, but it's got to be starred. So we have xj, A dagger xi star. Okay. And this is A dagger star ji. So this tells me that A dagger ij is AJI star, which was our matrix definition of the adjoint. Okay. So using nothing but our formal definition of an adjoint, as promised, it includes this matrix definition. Okay. Now, I mean, in this class, you might as well keep this in your back pocket and remember it. And refer to this written down, don't memorize it, but refer to it whenever you need to consider a general case. But remember, everything is isomorphic to matrices and intervals, so we can just remember this. Okay. Now, with the definition of an adjoint in hand, this abstract definition and its matrix realization, we can specify a special class of linear operators. So okay, so if A equals the adjoint of A, then A is self-adjoint. Okay. And this comes into more familiar varieties. If we are dealing with a real vector space with its inner product, then adjoint equals symmetric. Okay, that is that A is equal to its transpose. Okay? If it's a complex vector space with an inner product, then we call it Hermitian. All right. It turns out these subcategories, so we've got all possible linear transformations in a given vector space. All possible linear transformations. It's a huge number. It includes 0. They form a what? What do all linear transformations in a given vector space form for Rye? Do you know? You weren't here for it, that's why I'm asked. Now I asked you because I drew your card. But if I take all of the linear transformations on a given vector space into consideration, and I mean all of them, including 0, what does that set form? It forms a vector space, okay? But you have to include 0, which is the most boring linear transformation you can imagine, okay? These are subsets, okay, of those sets. These subsets are going to have really nice properties which don't hold in general for an arbitrary linear transformation. But those properties are one of the reasons why these kinds of transformations play such a critical role in physics. Okay, so we're going to specialize to special kinds of transformations for the properties which we're going to show you coming up soon. Okay? So let's explore some properties of Hermitian matrices really quickly. Actually, no, we'll just do this for arbitrary self-adjoint. Okay, so we can say if A and B are self-adjoint, so is A plus B. Okay? This is pretty easy to prove. We just say A plus B dagger is A dagger plus B dagger using the linearity of the adjointing. But if these are individually self-adjoint, that's just A plus B. Well, now everything in those brackets, daggered, is everything in those brackets. So the sum of two self-adjoint operators gives me back a self-adjoint operator. If I call this C, I call this C, that's C dagger equals C. Okay, so that's simple. If A is self-adjoint, so is alpha A for a real coefficient alpha. Okay? Obviously, alpha A dagger is alpha star A dagger. Okay, alpha's a scalar, so there's no point in transposing it, so it's just complex conjugation. But A is self-adjoint. Well, that is equal to alpha A if alpha equals alpha star. But that's what we specified right here, that alpha equals alpha star. Okay? And then last but not least, if A and B are self-adjoint, then AB is self-adjoint. It's boring, it is. It's self-adjoint. Is this true? Nope, there's an if. If A and B commute. Right? Why do they have to commute? Well, let's explore this. Well, I mean, that's the definition of commuting, but why do they need to commute?
Because when you take the dagger,
That's basically it. So let's do the if first. If we assume AB equals BA, so if we assume that they commute, then AB dagger equals, well, remember, if I'm daggering a product, that's the reverse of the dagger of the individuals. But these are self-adjoint, so this is BA. Okay. And then by this assumption, BA is AB. Okay? And then we can do only if. So we'll start with AB dagger being AB, and now we'll show that this proves they must commute. So we'll do AB equals AB dagger, which is B dagger A dagger, but that's equal to BA. Okay. So once again, I just want to point out, A and B can be self-adjoint, but unless they commute, their product won't be self-adjoint. Okay? Now, we've got this theorem up here, and we've used it quite a few times. just a linear transformation on an inner product space, but we've got these special classes of linear transformations we're considering. Symmetric, Hermitian, all these self-adjoint things. So maybe we can say something a little stronger than this. So let's see what that might be. All right, so I'm going to call this version 1. And now let me propose version 2. If A is self-adjoint, in a Euclidean inner product space. So remember, a Euclidean space is a space with a real inner product. A unitary space is a space with a complex inner product. So I'm just going to call it a Euclidean space. Then A equals 0 if AX equals 0 for all x. Okay. That looks a hell of a lot like this, except for one significant difference. And what is that? Daniel. What's different? Say it again? Oh, well, yeah. That's definitely different. This is looking at this subcategory of linear transformations. Okay. So for this special subcategory, this condition is actually strengthened. How is it strengthened? So this is any linear transformation in an inner product space. This is a result particularly for self-adjoints in Euclidean space. So there's a difference there in the set that you're dealing with, but what's the difference? What's the different conclusion? Anybody want to help them?
We're only dealing with one vector. We're only dealing with x for the self-adjoint case.
So you're
Well,
dealing with all x.
values of one vector. So like one basis.
Yep.
Not basis.
Go ahead.
Now we only need x, we don't need y.
So this is for all x and y. So this includes x and x,
Sure.
but it also includes a different vector here than here. It includes the same vector and different vectors. For this one, it's only if you use the same vector. Okay? Can everybody see why this is a stronger statement than this one? So it's like trying to think of a non-mathematical example of this being hold on, maybe I have it written down. I don't think I do. Yeah, no. So So let's suppose my set of vectors had 100 things in it, okay? And I wanted to argue that a transformation is 0 if this condition is 0, where I have to pair up every single possible pairing of those 100 elements. Every single possible pairing. Okay? That's very strong. I mean, that's a really complete condition for this thing to vanish. If every single vector that you put into it, or every single pair of vectors, sorry, gives you the same answer, then this is going to be 0. However, here, for that same set of 100 vectors, I don't have to consider all possible pairings. I only consider a vector paired with itself. So that's 100 of these expressions. This is a lot more. Okay? In particular, if I take two different vectors, then this doesn't have to hold. But it still means that A is 0. So you might just have to digest that for a bit. I found it was kind of difficult to appreciate the first time I saw it, so maybe digest it a bit. Okay. But this is definitely a stronger conclusion than this one is. All right? Now we can go further, because now we can say, for our third, if A is any linear transformation in a unitary space, okay, again, this is a vector space with a complex inner product, then A equals 0 if the inner product of x and ax equals 0 for all x. Okay? That's obviously a little bit stronger, because that's not looking at the subcategory of self-adjoint. This is any linear transformation. Right? Okay, so part of maybe understanding like why these are more limited, I'm just going to go through the proof. Okay, I was going to skip it, but I think we need to go through it. Okay, so first and foremost, for all three of these propositions, and I know I wrote this up earlier and said I'm not going to prove it, but I'm actually going to prove it. For all three of these, to prove necessity, that's the if statement, all we have to do is note. So this is necessity. Oh, right there. This isn't a necessity. If A equals 0, then xay equals 0 for all x and y, including the cases when x doesn't equal y. Okay? That's simple. That was trivial. It's sufficiency that's hard to do. Okay? So for sufficiency, we're going to have to start out with 1, this first case, and then we'll do 2 and 3 based on the results of what we get here. Okay? So now we want to go backwards. If xay equals 0, so now we're going to take this result and show that it implies that A is 0. Okay. For all x and y, then let's take the vector x to be the result of transforming the vector y by the linear transformation. And this is an arbitrary linear transformation. Okay. So one of the things we know about linear transformations on vector spaces is that they take a vector, they eat it, and they spit out another vector. Okay. So we're going to take x to be the vector that results from acting on y with the linear transformation A. Then what we can say is, all right, ay equals 0 implies that ay equals 0 for all y, therefore A equals 0. Okay. You follow? Okay. Now we can prove the second result. And what we're going to do is we're basically going to show that this condition reproduces this condition. So here we go. If xax equals 0 for all x, all right, then consider the following. X plus y, a acting on x plus y, equals 0. Okay, that's just a reflection of that. And then we can use the linearity. Okay. But this gives the following. X plus y a x plus y minus xax minus yay equals xay plus yax. Okay? And this has got to be 0. All I did was I took these two terms and moved them to the other side. Sorry, it's determinants. Okay. Now, if this is true for any x, what is this? It's 0. What is this?
0.
Also 0. And this? It's also 0. Okay? And that's why this thing is 0, the difference. So, this is true for all x and y. All right? But we have yax is axy star, which is axy, which is x a dagger y, which is xay. Okay? So I have that this is equal to this, which of course I can write as yax minus xay equals 0. I can take those two equations and combine them, and that will immediately tell me that 2xay equals 0 for all x and y. Okay. But we've already shown that a is equal to 0. Now, oh my God, let me get through all this. Okay, I have to pick my battles. Well, actually, I think we're just kind of, I'm going to go ahead and prove the third, and then I'll just have one more page of notes, and we'll save all this for next time. So my universal umbrella, I will unveil next Tuesday. read through the third. Part of this. Let's go ahead and erase this and regret it eventually. All right. So for the third part, we can actually use part of the second proof. So if xax equals 0 for all x, then following 2, we have xay plus yax equals 0 for all x and y. Okay? Now, since things can be imaginary in this case, let's take y to be iy. Then this becomes xaiy plus iyax equals 0 for all x and y. And then, of course, recall that alpha x beta y is alpha star beta xy. Okay, you only complex conjugate a constant, which is multiplying the first term in the inner product, not the second one. Okay, so we have ixay minus iyax, which is of course equal to ixay minus yax. Well, I is not equal to 0, so that's got to be 0. Okay. So adding this to what we had earlier, we find 2xay equals 0 for all xy. Implies a is equal to 0. Okay. Now, obviously, we can take these last two statements and combine them into a single theorem, which says, if A is self-adjoint, that is real or complex, then A equals 0 if and only if xax equals 0 for all x. Okay. So that's sort of our unifier of the real and the complex cases. All right. Now, why all of this? Well, remember, the world as we know it is real. I mean, when's the last time you were driving down the road with an imaginary velocity vector? Okay. When's the last time you swung a complex valued bat and hit an imaginary ball and knocked it across a real field? Shit don't happen. Okay. So if we want to use this in physics, we really need to be restricted to real things. But we're finding a lot of power in allowing ourselves to go to unitary spaces, complex vector spaces, consider Hermitian operators. We're finding a lot of mathematical advantage by allowing us to go to these complex spaces. Okay? So is there a way out of this? Is there a way to let ourselves go into complex land, but somehow we only get reality out? You all should be familiar with what I'm about to say. All right. Let me speak of two important important results that are just illustrations of why we can play around in the land of the complex. And as long as we are looking at subsets, not the full space of complex linear transformations and linear vector spaces, but just subsets, then things are good. First, a linear transformation A on a unitary space is Hermitian if and only if x ax is real for all x. We're on a unitary space. That's a space with a complex inner product. We're talking about a Hermitian matrix representation of a linear transformation. That's a complex matrix. But if I take any vector of the space, act on it with the linear transformation, and then take the inner product with the original vector, the result is real. Why is this important for physics?
Like to work in reality.
Say it again?
We live in reality.
Well, no, where have you seen this before? Where have you seen the fact that this is real? In what class? Quantum mechanics, okay? So, what we would say from the result of this is the expectation value of the operator A with respect to the state A. It's real. The expectation value of A is the expectation value of A. Oh yeah, the expectation value of A is what you would expect for the average in the measurement of A over many examples of this system. Okay? But we can do better than that. The eigenvalues of a Hermitian operator or transformation are real. The eigenvalues of a Hermitian operator are real. What are the eigenvalues of a Hermitian operator?
Observables.
Say it again?
Observables.
Those are the observables in quantum mechanics. Can you observe the Hermitian operators? No, you can't. Which is fine that they're complex. Okay? What you can observe, what you can measure, correspond to the eigenvalues of these things which we can describe by Hermitian operators. Okay? And they're always real. All right? So these are so important in our use of these that I'm going to prove them. So let's do it. We'll call this A, we'll call this B. So for A, for the if, we have if A equals A dagger, okay, if it's Hermitian, then x ax equals, and we can use the definition of self-adjoint, which a Hermitian operator is, sorry, this is for the inner product, and then we're gonna use the definition of the self-adjoint. So this is AXX. And then this is X, A, X star, because anytime you just flip around an inner product, you just have to complex conjugate the result. And then this is telling me that X, A, X is real, okay, because this is equal to its complex conjugate. It's real. Okay. Only if XAX equals XAX star, that is, if it's real, then I can write this as AXX, and then rewrite that as XA dagger X. Okay. Then what I can do is I can say, okay, this implies that X, A minus A dagger X equals 0 for all X. And that tells me what?
A 0.
What's 0?
Sorry, 8 minus 8 dagger 0.
Yeah, this tells me that A minus A dagger is 0, or A is equal to A dagger. Okay. For the second one, we can say AX is lambda X implies XAX equals X lambda X. Okay. But that lambda just comes out because it's a scalar coefficient. And then I'm left with the magnitude squared of X. But this tells me that lambda is XAX over the magnitude of X. Anybody follow that? What can you tell me about the nature of the numerator?
Real.
It's real. What about the denominator? It's real.
Positive.
Okay. Therefore, lambda is real. Okay. All right, I think I'm gonna end there, a couple of minutes early. Kind of sucks, but I'd have gone 20 minutes to get the last 3 slides. Are there any questions for Jake? None? All right, I'll see you all next Tuesday. And for those of you who send me emails, I'll forward those on to the grader, so don't, that's fine.